Alright, it's time for another math easy solution. Time to discuss a pretty interesting and useful topic on the logarithmic scale, and also later in the video I'll go over graphing in Microsoft Excel using this logarithmic scale, just to show that there's a easy to use option in Microsoft Excel to plot log scales. Now I'll get to that later in this video. Basically, a logarithmic scale or log scale is a non-linear scale that is commonly used when there is a large range of quantities. The opposite of this is just a basic linear scale, such as 1, 2, 3, 4, 5, or 10, 20, 30, 40, where you're pretty much incrementing by the same amount each step. And this is the opposite of that. And this one is, for the log scale, it's a multiplication instead of just an addition. So before we get to it, I just want to go over some common uses. These include earthquake strength, and you've probably heard of the Richter magnitude scale. So for example, an earthquake of 7 is 10 times stronger than earthquake magnitude scale of 6. And I think if you get to like 13, 14 or something like that, I'm not sure, I think that means the world's going to split in half, etc. So another one is sound loudness, and that's measured in decibels. The sound pressure level, SPL, measured in decibels. If you're watching TV and want to increase the volume, if it shows the decibels, just going from 10 to 11 is just about 10 times the volume. And also pH of solutions for measuring acidity or basicity of an aqueous solution. Aqueous is just water is the solution, and then you're dissolving something inside water. And anyways, I'm not going to go over too much on that. And also light intensity, that's also measured in logarithmic scale, and this stuff you could research on your own for further use. Anyways, so those are some common examples. So now let's get into the log scale. So the log scale is based on orders of magnitude rather than a standard linear scale. So each mark on the scale is the previous mark multiplied by a value. And this will all make more sense as I get later down in this video. So stay hold for that. And basically just a linear scale such as this one here, 1, 2, 3, 4, that's linear. A log scale is a multiplication, and I'll get to that as well. So the most commonly used log scale is a base 10 log scale or log 10 scale, like this. You could write it like that, and that is the one I will cover in this video because that's most commonly used. I've never actually used a different kind of scale besides the log scale and linear scale. So the purpose of the log scale is to more clearly represent values that vary greatly in size. So for example, consider the following table and its graph. So this is just a simple linear values right here, linear table and linear graph, where x is 1, 2, 3, 4, y is 10, 20, 30, 40. So you would assume this is just a straight line like that. So if we were to plot it, this is x, and there's our 1, 2, 3, 4. I mean, this is 1, 2, 3, 4, and then the values are 10, 20, 30, 40. So it's a perfectly linear graph. So that is a good scale just using these linear x and y coordinates, because it represents the data pretty well. So that's not a case we would want to use log scale. But now consider the following table and its graph. For example, this one, x is still a linear scale, 1, 2, 3, 4. But now we have y, which is 10, 100, 1,000, 10,000. So if we're plotting this on a linear scale as shown here, so the 10,000 is skewed super high up at the 4x here. We have this 10,000 mark, but this is 10 times larger than this value here, which is 1,000. And then that's 10 times larger than this. So from 2 to 4, we're going 100 times the size. And in fact, from 1 and 2, just looking at this graph, you cannot see the difference between these two. It looks pretty much identical, but they are. But number 2 is 10 times the size of number 1. So that this graph doesn't really tell us much between these low values. Besides that, the 4 is super high above it. So now the y values, again, as I stated, vary greatly from each other, and by looking at the graph alone, it is difficult to compare the values properly, especially the values at x equals 1 and x equals 2. Those are those values right there. Since the y values vary greatly, we can try converting them to a log scale. To do this, we simply find the new values and then plot those log 10 of y, or basically log base 10, plug in their y and see what we get. And the idea behind this is the fact that the log base 10 of a number is the value of the value of the power of 10 to equal that number as shown below. So basically that's where this base 10 comes in. So what we're going to do is let z equals to this value, this log base 10 of y value. And now, recall from my earlier videos on logarithmic functions, what we have is, if we write something like this, the definition is basically stating that this base 10, and then this z is the power to it, this equals to y. So this is what this function is defined as. So if we have 10 to the power of z equals y, and basically the z right here, the solution, the function is written as a log base 10 function. So it's like an inverse function. And basically I'm using z instead of x because x, let's be consistent in this video, x is just for this x coordinate. So z is the logarithmic, is just a new scale, is a log scale value. So if we have something like this, so let's say, so if y equals to 10, as shown here. So our first value y is 10. So instead of writing y is 10, what we have now is z is equal to log base 10 of 10 here, and this equals 2. In other words, this is the z value right here. So remember, log 10, 10, these just cancel and become 1. And in fact, that's what it equals to. That just equals to 10 to the power of 1, which is just 10. And so our z is that. So if we have instead y equals to, let's say, 100, same idea. Our z, our new scale, is going to be log 10 of this is going to be 100. So in other words, this equals to, this is going to be equal to 2 actually, because remember, 10 to the power of 2 is just 100. So we're moving, so now instead of plotting the actual values of y, we're plotting what values of the power. So that's where it is right here. So the value of the power to equal that number, that y number right here, put a bracket, y. So that is what we're plotting. So instead of plotting 10 and 100, we are plotting 1 and 2. So notice the difference. And this is 10 times the size, but this is just one difference in size in the increment. And now, same thing if we go over to, let's say, 10,000. See, what was the next one? 1,000. So if y is equal to 10,000, so z is going to be equal to log 10 of 10,000, and this equals to, well, 4, because this is just 10 times, 10 to the power of 4. 10 to the power of 3 would be at 1,000, and then just going in between like that. So yeah, so now if we get those tables back here again, this is our x and y. That's this values right here, 10, 100, 1,000, 10,000, right here. Scroll back up. So what we're going to be plotting now is instead we're going to be writing these. So each one of these can be written as a base 10 power. So 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, like that. And again, what these equal to, this is just 10 times, well, that's just 10 by itself. This one here is 10 times 10. This one right here is 10 times 10 times 10, just to show you that it's a multiplication. This is 10 times 10, so it's 4 times. So this is a multiplication, and that's where we get this statement right here. It's multiplied by a value. In our case, in a log 10 scale, that's by multiplying each one by 10. So we're always multiplying the previous one by 10. This one's 2 tens and 3, then 4, and then then if we go to 100,000, that's just a 5. And now if we were to, I'll just put an arrow like, a line like this, and now let's graph let's just write down our log 10 of y, like that. Let's write this neater. Log base 10 of y, that is this one here. That's just these values right here. Remember, is just the value in the power of the base, which is 10. If it's a 5, you're going to use a base 5, etc. So this is going to be like that, and this will be 1, 2, 3, 4. So yeah, so now if we graph the same y values but on the log scale, we get a much clearer graph. And that's shown right here. So this is the log 10 scale right here, and that's on the right side in red, and the previous, just the unchanged, just linear scale is the black one right here. So remember, this is the exact same plot. The black value is the exact same plot before, just looks something like that. So basically the idea is, instead of dealing with something that looks like this, we change the values here on the right side so that we can easily see that it seems like it's a linear plot. So the idea is to make it more of visually appealing, and now we could easily see that the value from from here at x equals to 1, this value on the log scale is 1, and then 2 would be over here. So the difference between here and here is 1, but it's actually 10 times larger. Alright, 10 times larger. As opposed to here and here, you have no idea how much larger it is. I'll put a question mark like that for there. And now what you could also do is, instead of just writing the log values here, you could actually just put in those values here. So this at 1, this was at 100. I know this is just 10. That's 10 to the power of 1. This is 10 to the power of 2. This is 10, 3, etc. So instead of looking at it like that, so you can convert it back into there, but still keep the same scale. Like that. Put a 3. This is 10, 4, etc. And this one is 100,000, which is 10, 5, like that. And I'll get to that in a bit with the Microsoft Excel sheet that I've made. So now another topic I want to go over, or another part of the log scale, is a log plot. And this is a plot that has both vertical and horizontal axes scaled logarithmically. And that is like this right here. So let's say if we had x, which is 10,000, and this is 1,000, 100,000, and this one is about, I think, 10 million. Let's see, 3 zeros, 1, 2, 3, 3 zeros. So 10 million, then y is again like this. So something like this, we would use both of them. It's better to scale both of these to get a better graph right here. So this one here I've done in Microsoft Excel. I'll get to that in a bit. And notice here we don't have to write actually log. We can still use the y and the x values, but notice how it goes from 1 to 100 to 10,000, and this one's to a 1, 2, 3, yeah, 10 million. So the scales could be different here. This is multiplying by 100 each time, I believe, instead of just 10. And also the in between here, the minor values are also changing more and more, because as you get further to the right side, the differences change dramatically. So, and also here from here, 10, if this is 100, this is 10, this would be actually 20, this would be 30, and then they get smaller and smaller. So basically 90 and 10 are very similar, and then going all the way up to 10,000 like that. So in Microsoft Excel, there's an option to scale any axis, so misspelling, any axis logarithmically, and I'll get to that right here. So this is the Microsoft Excel sheet. I'll put the link to this in the video description below, so you can download, play around with it. So this is the first linear graph. Here is plotting the graph both linearly and as a logarithmic scale like that. And also the other thing I wanted to do is yeah, this part right here. So this graph is actually the same as this one, but I just need to change it up a bit. So we could change this, and the way to do that is, so you would right click here, usually just go to format axis, and it should pop up. So you just, in Microsoft Excel, you just click this logarithmic scale, and you can also change the base as well. So this is from 2 to 1,000. I think if it's 1, it's the same thing. So actually no, I think 1, you'll just get the value 1 all the time, so it doesn't work. So, and then for this scale as well, as you can see, it's hard to read these still. We'll change this into logarithmic. So you just right click, click it, and then you just click it and it changes. So notice how we just change it. It's the same value still, just all we're doing is plotting it differently. So, yeah, actually one more thing, to get these grid lines in there, just to show here, to get those, you just right click here. I think it's a format, or there should be an add button. Let's click format here, click solid line. This one's black here, I'll make it gray, like that. Same thing here, just click here, it's on the format axis side, solid line. No, right click actually, let's go back here, format axis, whoops, format axis like there, and then go to the grid lines. Where's the grid lines? Actually no, format, grid lines minor. So the major ones are these big ones, 10 to 100. Yeah, okay, and change that color. Okay, something like that. So there it is. That's should be the same color as I had here. I had the default, it's a bit lighter. But anyways, that's the idea. You could just play around with Microsoft Excel. Some cool stuff you could do in there. And also another note that I wanted to make is that only positive values can be interpreted on a log scale, because log of y is not defined for negative values of y. For example, in our case, let's say z is equal to log 10y. Then remember, by definition, you have 10 to the power of z is equal to y, and basically this 10 to the z is always greater than 0. 10 to the z, you can't go to 0. The only way is basically if you take the limit as y, actually not y, so only way to get this 10 to the power of z going to 0 is, because it's always positive, 10 to the power of anything is always positive, as if you had limit as z approaches negative infinity of 10 to the z, what we end up having is this 10 to the z, actually 10 to the infinity, 10 to the negative infinity, like that. This is same thing as writing 10 to the power of, 1 over 10 to the power of positive infinity, and this is just approaching 1 divided by a large number of 0. So that's the only way you're going to get a 0 like that. And also if you graph it, again, make sure to watch my earlier video on logarithmic functions, it's pretty useful. So this is y, this is z, again just using our zy, using this as the x-axis, just because we already defined x as the x-axis and before, I don't want to confuse anyone. So the graph actually looks something like this, where this is our z equals 2 log base 10 of y, like that. And basically, as you can see, this is approaching 0 but never actually reaches it unless you go to infinity. And also at this very point right here where y is 0, this is the 0 value, this is y is 0, this is when y is 1, and then the z is 0. So at this point is actually 1 and 0, like that. And that's because, well, this is just saying 10 to the power of 1, 10 to the power of 0. Yeah, actually, so this just means 10 to the power of 0, which is our z value, equals to y, which is our, equals to 1, which is our y value, like that. So remember, z is always the power of, it's always the power in the base, which is in this case 10. So something like that. And also if you try doing that in this calculator, you'll get that same thing here. So put a negative here, and now, so we get an error, negative or 0 values cannot be plotted correctly on log chart. Only positive values can be interpreted on a logarithmic scale. So, and then as you see, there's no value here, so just ignored it like that. So anyways, that is all for today. Hopefully you learned from this pretty interesting video on the log scale. It's actually very useful. I use it a lot, especially in university and otherwise, especially when I've tried to analyze random data. Sometimes you'll see that large scale data that just varies a lot. Log scale is actually pretty useful. Anyways, that's all for today. Hopefully you'll learn. Like always, you can download these exact notes and the Excel sheet in the links below in the description, in the video description. So anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.